So empirical risk minimization is a reasonable idea. But when you do this, the training error, which is just the empirical risk, now becomes a biased estimate because you've used it to select your parameters, right? So if we look at our training error, this is the minimization, this is the minimum training error with respect to our selection of our parameters, right? And this is not necessarily going to converge to the risk in the large data sample. Sometimes it does, and this is when a uniform law of large numbers holds. But it's not necessarily going to be the case that it converges, and it certainly isn't an unbiased estimate anymore. So before, when we fixed our theta, then Rn is an unbiased estimate of R. But because theta is selected to minimize this Rn, if we look at, for example, the expectation of Rn of theta hat, that's just the expectation of the minimum of Rn of theta. And that's not equal to the minimum of the expectation of Rn, which is the minimum of Rr. And really, we want this minimum, the minimum theta, the theta that minimizes the true risk, this R. But of course, our empirical risk after we do the minimization is not going to be an unbiased estimate of the true risk. And this sort of makes sense. If you're using the training data to select your parameters, then you're not necessarily going to have that your empirical risk, the training error, is unbiased. It's going to be typically biased downwards. Right? Okay, so the solution to getting both a good estimate of theta, or selecting theta using empirical risk minimization, and getting a good estimate of our true risk, is to do a training test split. We train on our training data and we test on our test data, and then we can get some decent estimate of the true risk because they are split, and hopefully the two data sets are independent of one another if we're in the IID context. Okay, so I had that data set before. I'm going to do this by hand. Before we did it with scikit-learn, just once, I'm going to do it by hand. And so let's take our X, we'll randomly shuffle the indices, and then we'll select the first third to be our training set and the second third to be our test set. Okay, so we're going to fit on our training data. We're going to predict on our test data. This is using our fit and predict methods that I constructed, the defs that I constructed by hand. And then we'll compute our losses for the test data. And then let's also do it for the training data, right? Okay, if we look at our training losses, we have effectively 0 all the way down, right? So these are the losses over the training data. And remember, this data set, each of these samples corresponds to a country, and we are predicting the life satisfaction using all the other indices in this data set. Okay, if we look at our test losses, these vary quite wildly, right? And the losses are in the thousands. Right? If we look at if we average the training loss, this is effectively 0. So this is our empirical risk. And if we average our test loss, this is huge. So there's a massive discrepancy between the training and test data set. And when we think about this, it's actually quite natural what's happening because the amount of data we have is 36, which is roughly 3/2 of 24, which is the number of predictor variables. So when we do our 2/3 training test split, we end up getting roughly the same N and P are roughly the same number of data, same number of samples in our training set as number of predictors in our training set. And we know that linear regression will, we can look at, maybe we'll get to this later on, we know that linear regression will start to interpolate through the data points when the number of dimensions is close to the number, or is the same as the number of samples. And so we end up getting zero training error. But if we had used training error or empirical risk as our measure of the quality of how good we're doing, then we would have we get a very poor estimate of the true risk, which is closer to on the order of thousands in this case, right? So, so training test splits, very important, because that's the only way we're actually going to get a reliable estimate of our risk, is after we fit on our training data, is if we've held out a test data set. And this is how we can think mathematically. What I went over before is how we can think mathematically about training test split and the need for training and test splits. Is that there's some true risk, which we're trying to minimize. The training error is a decent surrogate for a fixed parameter for the true risk. But then, because we minimize that training error, we can no longer use it as an estimate of the of the true risk. So that's why we use a test set. Okay, so let's do this for the wine data set. So we'll return to the wine data set. We'll do the same thing. We'll fit, we'll predict. So we could use the code we did for the beginning of this, but I just wanted to reuse the same code we had before. And if we look at the average training loss, which is the empirical risk, this is 0.412. And if we look at the average test loss, so this is the test error, this is 0.424. And so because we were doing linear regression and in the case of the wine data set, n is much bigger than p, the number of samples is much bigger than the number of predictor variables, we get that the training loss, even after we fit, is almost the same as the test loss, but it is biased downwards. So it's consistent with what we know to be true about training loss, average training losses, is that the losses are smaller than we should expect if we hadn't fit on the training data. But since we have a lot more data points, these are actually a lot more similar. But there are two things that this was dependent on. So it was dependent on the size of the number of samples, right? And we saw this because the wine data set has a lot more data, has a lot more samples than the life satisfaction data set. And so we had the training loss, the average training loss, the training error, and the test error were much closer for the wine data set because they were larger. But we're going to see in the next lecture that this also depends pretty heavily on the method we used and how much this method is going to tend to overfit. So in the context of linear regression, it tends not to overfit relative to other methods quite often. Of course, this was violated when the number of dimensions was roughly the same size as the number of samples, right? But we'll look at other methods like k-nearest neighbors and methods with tuning parameters that allow us to tune how much the method overfits. And then we'll see again that having a training test split is essential to effectively calibrating what the true risk, estimating what the true risk of a method is.